rose powder, right?
Yeah.
Can y'all see your attendance on Canvas? Man.
I see the other classes, so I assume
I was just wondering. $100 $100 was it? Yeah. Yeah, you always here. Most of the time. I think he missed a couple times. He was sick or something.
Yeah, that week.
Yeah. So I think we did, so we're in chapter 3 now, right? Yep. What time is it? 11 o'clock. Got 6 minutes. Oh. Lost my damn thumb drive. Man. Found it. Thank God. Thank you, God. All right. Touch her right there. You told me you need to take the test. You need to take the test. What's your name? Jayla Franklin. All right, so we're in chapter 3 now, momentum and energy. So we discussed the lecture slides on Monday. All right, and so if you need to review those, they are available for you on Canvas. So you can download those from Canvas and you can review those if you choose to. All right, but today we are going to go back over chapter 3, right? Except we're going to solve problems in chapter 3. Same as we did chapter 1 and chapter 2. All right. First, we'll just we'll just go over some important equations that I think you should pay attention to. All right. But all of this is covered in the lecture slides, but I'll point it out if for those of you who need more clarity. All right. So we have momentum, right? We got momentum. Momentum is P M V, right? And M is mass. This black might not be showing up pretty good. Mass. And V is velocity. All right? That's pretty straightforward. Let me see if I'm showing up on the camera here. Maybe not. Right outside. Nope, a little bit this way. All right. So mass and velocity, right? We're calculating momentum. Okay? And and we have impulse, right? Momentum. We have impulse. Pulse. Impulse, and that is FT, right? So impulse is FT. It's also defined as the change in momentum. Okay. So impulse, right? So impulse. So we can call it whatever you want to. We can call it I. I is equal to the force times the time you apply it, right? Which is also a change in momentum, right? That's what impulse is. And we recall what I said about the boxers, right? So, we got elastic versus inelastic collisions, right? Inelastic, elastic collisions are like rubber bands, right? That's why it's elastic. That means all energy elastic, well, y'all know them, elastic collision, right? And let me write it, make sure I write it correctly. Okay? When objects collide, objects collide without generation of heat or deformation of objects, right? And we have inelastic, right? Inelastic collisions, right? And inelastic collisions characterized by, right? Characterized collision is a collision characterized by the generation of heat or deformation of objects, right? And what did we say the example of an elastic collision was? The billiard balls, the pool balls, right? Billiard balls, right? So example, billiard. I don't know how to spell billiard. I think that's it. I don't know. Billiard balls. Pool balls, y'all. Pool balls. Okay? Billiard. I think that's how you spell it. I don't know. And what's the other one? Inelastic. Car crash. Right? Car crash. That's an inelastic collision. Car crash. Right? And so we also talked about conservation of momentum, right? Conservation of momentum. What does it mean to conserve? What does that mean to conserve? That's the root word of conservation, right? What does it mean to conserve? To save or not to waste. So if conservation of momentum means what? Huh? Right. The same momentum we had before the collision must be the same momentum after the collision. So we say mass times volume before the collision, has to equal mass times volume of the objects after the collision. Okay? That's conservation of momentum. Right? We also had what? Conservation of energy. Yes. Conservation of energy. And what does that mean? Huh? Save energy. So that means what? The same energy I had before the collision must be the same energy I have after the collision. So how do we define total energy? There are two types of energy we talked about. What are they? Kinetic and potential. Right? So we have kinetic energy plus potential energy before collision. And we have kinetic energy plus potential energy after collision. Right? This is how the roller coasters work, right? Roller coasters work by this principle right here, conservation of energy. Right? When I'm on a roller coaster, I roll up, way up, way up, way up, way up. Then I get to the top, and I sit there for a second, and then I do what? So all of the energy I had at the top right here is potential energy. And then when we drop, it's going to all turn into what? Kinetic. Okay? And then when I hit the ground, and then I do what? Go back up. So all of that kinetic energy is going to start to turn back into potential. Okay? And the same is true for conservation of momentum. The same applies. Right? So we also talked about work. Right? Work. Doing work. And how do I do work? How does work get done? Huh? Well, it's an equation. Force times distance. Force times distance. All right? What's your name right here? Crystal Carter. Trinity Smith. All right. So work equals force times distance, right? So in order for me to do work, I must apply a force, and what else must happen? Has to move, right? Has to move. You remember what I said about pushing the wall, right? Even though I push on the wall doesn't move. Have I done work to it? Yes and no, right? But if we have taken a physics class, then we understand that there's two things going on, right? So I have done work, but the work that I've done, right, is counteracted by the force that the wall puts back on me. So therefore, I have an equilibrium situation where nobody moves because our forces are equilibrated, right? Y'all remember equilibrium, right? All right. So force, so work. So in order for me to do work, I must have a force, and the object must move a distance x, right? Move a distance. That's d. I shouldn't say x. A distance d. That's how you do work, right? When you're lifting weights, you got to move. In order to do work on the weights, you got to move them. If you didn't move them, they don't move, you don't do work, right? But you know that if you're standing under something that you can't lift and you try to lift it and it doesn't move, you know you still did work, right? It's just, well, you didn't do enough work to move it, okay? So that's work. We also had power, right? Oh, let's go over. Sorry, I went a little bit too fast. Right. So let's do kinetic energy and potential energy. Right. So kinetic energy is what? Anybody know the equation for kinetic energy?
KE equals 1/2
Yes. Well, uh, it would be mv squared over 2, right? That's what you said essentially. Really, it's 1/2 mv squared. Okay, that's how I remember it. It's the same thing as saying 1/2 mv squared, right? That's kinetic energy. So M stands for what? Huh? Mass. Right? So it's important. So this is how you create study guides, folks. This is what I'm showing you. So the next, when we come back on, what's the day? Wednesday? When we come back on Friday, then the next step in creating a study guide is we're gonna solve problems. That's how you do it. You go through this and you identify everything and you make sure you know what this is, what that is, what this is, what that is. You got to get that first. Okay? And then you solve problems because that's what you're going to have to do on the exam. Okay? So potential, this is kinetic energy, right? What is potential energy? Anybody? Huh? Mass times gravity. What's your name, man? What is it? I can't hear you. Jalen? Dalen. Dalen what? Huh? Wilson? Okay, Dalen Wilson. And what's your name right here? You. Yeah, you. Antonio Sanders. All right. MGH. Mass times gravity. So let's write these. Hold up. Mass. M is mass. V is what? Velocity. So how fast something is going, right? Velocity. So what is it here? M is what here? For potential energy? Mass. G is what? Gravity. And H is what? Height. Right? Because why? Because potential energy depends on what? How high you go, right? That's why I tell you about the skyscraper. You go stand on a skyscraper, it's going to feel like, when you look off the side of it, it's going to feel like the earth is pulling you off of the building. The taller it is. That's because that's a gravitational pull of the earth saying, come back to earth. Okay? So, what else? So we got that, we got work, and now we got power, I think. Yeah, we got power and we got work energy theorem, right? So, yeah. So work and energy, right? Right? In order to do work, we need energy, right? That's why you got to get up in the morning and eat breakfast, right? Because in order to do work, to get out of your bed and come to class, right? There has to be a force applied somewhere, and you have to travel a distance to get here. So you got to do work to get here, right? And so that work requires some energy, right? So if you're the type of person, right? Well, you know, like I say, some people, because I don't eat breakfast, all right? But, you know, I do other things in the morning, right? but you need some energy. That's why it's like that. That's why you should eat breakfast in the morning, because you need the energy. That's gonna be converted to energy so you can do work. Same way you got to put gas in your car in order for your car to move. Gasoline is converted to energy through combustion. Okay? So there is a theorem called the work energy theorem. Right? Then that just essentially says that work and energy are the same thing. Right? So if I have energy somewhere, if I require energy, like I said, if I require energy, or if I require some work to be done, right? Like in an elevator. When you move in the elevator and go from the first floor to the second floor, somebody has to do work. You didn't do it because you didn't move yourself. Right? It's a machine. A simple machine that's doing work. Right? But that work is the energy that is required to move you, or the energy required to run that machine gets converted to the work used to move you up and down, well, up in the elevator. Where's the work energy? There it is. Work. All right, so I'm gonna erase some of this. I'm running out of space here. Let's start here where I started it. All right. So work energy theorem, right? Work energy theorem. Just says that what work, which is force times distance, is equal to change in kinetic energy. All right. Change in kinetic energy, right? Because oftentimes, if, right? So before an object moves, there's no kinetic energy. So then that means what? If there's no kinetic energy, then that means there was no what? If this is zero, then that means what? If that's 0 too, they equal. So if there was no work done, or there was no energy, then that means what? There was no work done. Y'all following what I'm saying? They are the same thing. So in order for work to be done, there must be a change in kinetic energy. Okay? So when you get in your car and it's still parked, there has not been any work done because it has not moved anywhere. But once you move your car from point A to point B, some work has been done. The work that was done from moving your car from point A to point B comes from the gasoline that was burned during that process. So that's energy. Okay? So it's work energy theorem. Okay? So F is force, right? But we already described all of those terms. That's just combining two different things, right? Kinetic energy and work. So that's why you remember it's the work energy theorem. That shouldn't be too hard to commit to memory. Okay? We got this stuff about machines and efficiency. right? Of course, what is efficiency? Anybody? What does it mean to be efficient? So tell me what the equation is for efficiency. No, precision, that's different. But tell me what the definition of efficiency is. What does it mean to be efficient? Huh? Well, it's something like that. That's close, right? It's energy output. Energy output over what? Total energy input, right? Yes. So total energy input, right? Energy output over total energy input, right? So there is nothing that is 100% efficient, right? That's like being perfect, right? There is nothing on earth that is 100% efficient. That's against the laws of thermodynamics.
What is it? Total what?
Total energy input. So basically, how much bang do I get for my buck? You understand what I'm saying? Like how much I paid and how much do I get? This is what I get, this is what I paid. You following me? So that's what efficiency is. And that's gonna be in terms of energy. And like I said, we're gonna work some problems and we're gonna do some specific examples and give you a little bit more clarity about that. But that's efficient. That's essentially what it is, though, right? Is how much did I pay, and what did I get for what I paid for? Right? Just like in economics, right? You get what you pay for. That's the same thing here. It's the same principle here. Rarely are you gonna get, right, all your money back. Whatever you pay, whatever you buy, somebody has to make a profit off of that. So you are how they make a profit. So you're not paying the same price that they pay for the object. This is free enterprise economics, right? So that's how you think about that. Is that when I buy something from the store, in order for the store to make money, I can't get everything back for what I paid. Because then the store can't make money. Duh. Right? So it's the same thing here with energy, though. With energy. Right? And a lot of times, what? We lose efficiency. Let's take, for instance, with the car. Right? We know the car, we only get about 30% out of a full tank of gas. That's about how much you actually use when you fill your gas tank up. 70% of your gas tank is being wasted in heat and all kind of other stuff. Right? So that's not a very efficient machine. Okay? All right. What time is it? I feel like I've been talking for a while. 11:30. All right. And so now we have sources of energy, right? Which is gonna lead us to the end here. Sources of energy, right? Sources of energy. Anybody? Name a source of energy for me. Sun. And what do we call that? Solar energy. Solar energy. Where else can we get energy from? Wind energy. What else? Hydroelectric energy. Yes, sir. Hydroelectric. What else? Huh? I can't hear you. Huh? Sound. Yeah, you can get sound energy. Yes, you can. It's hard to capture sound energy and then use it for something. Kind of like heat. Heat is another one that's kind of hard to capture. But yeah, you're right. Sound has energy. Yes, indeed. When you hear a plane, if you hear a plane pass by you on a runway, and you hear that, you will feel that, right? Because that sound is very. Now, the sound of me talking to you and stuff like that, you might not feel that. But there are certain sounds you can feel. Okay? What you was going to say? You about to say something? Oh, okay. Anybody else? You said coal? Yes. Like you talking about fossil fuels. Right? That's like digging into the earth. Right? So sound. And that'd be what? Fossil fuels. Right? Like gas and oil, what we do in Louisiana, right? That's why we suffer so much from hurricanes, right? Because digging for oil and all that kind of stuff off the coast, right? It ruins the ecosystem. And part of that ecosystem protects us from hurricanes, right? Or they take some of the brunt of that force. But when they're no longer there, then that comes to us directly. All right. So we missing maybe a few more. Right? Now everybody in here, y'all missing the most obvious one, the one y'all probably couldn't live without. Huh? Well, huh? I know. What can't y'all live without? Huh? Your phone. And what do you need in the phone? A battery. Batteries. Right? Batteries. Okay? Batteries. That's very important. Right? For all mobile applications. Anything we do where we can't sit still and get energy from the power plant, like plug into the wall, we need a battery. Right? And there may be more. I might be missing one. The last one, right, is a fuel cell. Right? A fuel cell. Anybody know what a fuel cell is? Nope. Nobody ever heard of a fuel cell? Nobody? Okay. Well, a fuel cell, it'll eventually replace the engine in your car, right? And it uses air and water to produce energy. Okay? Well, that's one type of fuel cell that does that, but there are many types of fuel cells. But all of them produce energy without using gasoline or internal combustion, which is an inherently nasty process which pollutes the environment, right? And contributes to global warming and all of that stuff. And that's the reason why we see hurricanes like Katrina, right? It's because the temperatures in the ocean are very warm because there's a bunch of soot that sits around the earth like a blanket. And so when the sun sends energy, solar energy, the sun is sending solar energy to the earth, it bounces off the earth, and then that soot that's around the earth from you driving your car every day, carbon soot, it's around the earth like a blanket. And it traps all of that energy, and it does what? Heats the earth up. And that's why the hurricanes are getting stronger and stronger and stronger, because we're getting hotter and hotter and hotter. Right? But then you have some folks that say, oh, well, sometimes we get very, very cold, right? But that's just the natural cycle. That's the balance. That's God's balance, right? As much as you get hot, you're going to get cold. That's the balance of life, of everything in life. There's balance. All right? So we just created a study guide for you, or the beginning of a study guide, okay? And so on Friday, like I say, what we're going to do is we're going to go through and we're going to solve some problems in chapter 3. And then we're going to be done. And we're going to go to chapter 4 because we got to go. We got to keep going now. All right? So y'all got this process? Yeah, this is how we're going to go for the next few weeks so we can get to at least 6 or 7. Okay? All right. Thank y'all.